Good morning, everyone. Thanks for coming instead of staying sleeping. I really appreciate that. I know it's hard because it's 9 a.m., but really appreciate it. I'm Carlos. I'm the head of AI at the Forta Foundation, and I'm going to be explaining to you today how we are using AI to actually prevent malicious transactions. And yeah, in blockchain, I know AI, blockchain, I'm a big fan of saying these keywords. I promise there is only one more over the presentation, but it's going to be fine. So first of all, I want to give you a little bit of context of, because now I'm talking AI for prevention, but Forta started a couple of years ago with monitoring. So we started using machine learning to analyze blockchain activity. And we were looking at how a particular address was funded, the smart contracts they were deploying, and we were using machine learning in several different flavors to be able to detect when something was going to be attacked. But we were doing monitoring, right? Which means that we were finding that someone was potentially an attacker, and we were saying, you have an attacker here. But that's it, right? And that's not so enticing. It's not so interesting because, yeah, OK, I know that's an attacker, but I don't have any of these tools to actually stop this attack. Today, we are moving a little bit forward, and instead of just using this previous part that we were commenting of, we are looking at funding, we are looking at the smart contract that they are deploying, we are just directly screening the transactions themselves to try to identify whether a transaction is actually performing an attack or not. One of the things about detection, especially in these last couple of years, is a lot of people have been working on this thing, and detection methods have been gotten much better. And a lot of attacks that before we were not able to detect, now we are able to detect before they actually incur into any losses, right? But we are able to detect does not mean that we are able to stop them. And even in cases when we can see an attack and we say, like, OK, this is coming, you might even start losing some of the funds because like a couple of transactions already went through and you were a little bit too late. Plus, there is the problem of there is not a very strong mechanisms on what to do to actually stop these attack transactions, right? Because you can stop your protocol, but then it comes with a lot of other problems. The people cannot do like normal operations, and you are just like blocking completely, and it's like a very extreme measure. So we think that there is a better way of doing that, and this is what we are introducing as Forta Firewall, which mostly what it's doing, it's like it's looking at the transactions from a stateless point of view. And this is something that I'm going to spend a lot of time afterwards because I think it's really interesting and it's really important in order to be able to stop transactions. And this system is actually able to block these transactions before they are happening. We are not talking about pausing the protocol. We are not talking about further influence, that literally just stopping the transaction itself, that it's an attack transaction. So there is no other problem to operations other than you are not losing your funds. That sounds amazing, right? Great. So now let me give you some more information on, I have stateless here. I'm going to explain why I mean by stateless at this point. And I'm going to also explain a little bit to you how to create these AI systems and what to do with them, what's the process to improve them, how to validate them, and so on and so forth. So great. By stateless, now imagine that we are looking at a transaction. And we are just looking at a transaction, right? And we want to identify whether that transaction is an attack or not. Like, is it behaving in a different way how it's supposed to be, and someone is gaining money or funds or whatever in an illicit way? Yes, then we stop it. Easy, right? Well, not so much, otherwise we would have already been doing it, and no one would lose anything. But let's look at the transaction itself. What do we have there? We have what we are using to generate this transaction, which is like who is sending the transaction, right? Where it is being sent, and what is being sent. So the data and the state of the chain, like you need the block number just to have an idea of how things are there. OK, that's your input. You have nothing else. Then what you can do is, using that information, since it's deterministic, you can simulate your transaction. And then on top of having the from, the to, and the input data, you would get the logs of what actually happened in the transaction and the traces. So who is interacting with who, like who is sending like whatever delegate call to whoever other contract, and all that information. And that's it. That's all the information that we have, right? It's quite different to how a normal person right now, a security researcher, would go into a transaction and identify, OK, this is an attack, or this is not an attack. We are just looking at the transaction. And actually, in my opinion, this one has a little bit of a problem also, because we don't necessarily want to stop people just because of who they are or who they interacted with to actually stop things, right? So just because you are a person that was interacting at some point with Tornado Cash doesn't mean that what you are doing in this particular moment is actually legit, and you just want to be completely anonymous. You don't have like any malicious intent. So just the fact that you are funded by one of these mixers doesn't mean that necessarily you are going to have this illicit content, right? So the from and the to, even though we are using them as flags because it's a lot of valuable information to know within the interaction who actually started the transaction, right? Like we know that a certain address actually is the one that is doing this call to this other address, but we don't have any extra context about that address. We just know that this is the address that initiated the transaction, and that's it. We don't know anything about it. So this is what we mean by stateless. Like each transaction is stateless, is completely independent on anything that has happened before. And this is something very interesting, because let's compare it to how a stateful, or like how right now any security researcher would understand what is an attack. You would see a transaction that is weird, that you have like there are a lot of funds moving and so on and so forth. And then you would go to the address that is starting, you would check their funding, you would check whether it's coming from a mixer, whether they are like coming from other illicit accounts, like how are they getting funded, how are they getting their initial money. What is their past behavior, right? So are they doing also weird stuff? Do they have like a history of scamming people before and it is known? Or do we have like any extra information about what this address is doing? Or like which smart contracts have it deployed? We can analyze these smart contracts. We can see whether they were good or bad. They were potentially malicious. If they have a story of deploying malicious smart contracts and were funded by Tornado Cash and had already scammed people, then, well, I guess this person is probably a scammer or an attacker, right? So it's kind of dangerous. And then we also have like some heuristic rules of like, OK, you are completely emptying the pool, blah, 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 that it's like either very general or very protocol specific. So in the end, what I want to say here is that this is a lot of extra information that we are taking into consideration, right? And this is what we are considering by stateful detection, because we are taking into state the previous state of everything that has happened, and we need to have all this context for transactions and so on. But having this context obviously helps, right? Because it's always nice to have more information about it, but it's slow. Like whatever you do, you have to have this thing somewhere. You cannot have it like you cannot have like a huge memory with all the others and understanding what each one of those is doing. So even if you have like a nice system where all of this is together and you still have to call it, you are still adding like a couple 100 milliseconds for every transaction that you are trying to detect. And when you want to go at a proper scale and you want to go more to, like when you want to be working on a rollup instead of just protocol specific, that is just too slow. You are going to potentially break the stuff, and this is something that it's just not acceptable to be that slow when you're doing this thing. So this is why doing stateless and just looking at the transaction itself, it's really valuable, right? It has like these two main points of, first of all, it's faster because all the information is already there, and you just need to run code over it. Plus, there is the, I completely lost my line of thought. Whatever. Cool. So now let's go to how we can train a machine learning model up until now, right? This is a very standard machine learning life cycle of what you would do. And here you're going to have to apologize me. I'm going to use the word model a lot, and it's going to mean two different things. Because like you have the model of when you're modeling the data and the model of like the deep learning model when you're doing inference. I'm going to try to do deep learning model. If I don't, you can hate me afterwards. You can find me for a coffee and should throw it in my face because it was confusing. So great. So how do we start? We have the transaction, right? And we have like the from, to, data, logs, and traces. And that's it. The first thing that we need to do is model the data. And that in this case, model the data means we take whatever input data that we have, and we transform it in a way that it describes our transaction in a unique way. And it has a format where it can be passed to a machine learning model, in our case, a deep learning model. Like deep learning models here, and in this talk, when I'm talking about AI, I'm not talking LLMs. LLMs are not necessarily the best tool for this job, but AI is a bigger umbrella. There are other type of deep learning models, which is what we're actually using. Just imagine what we have been seeing like some years back, this computer vision, we were identifying things there. The model of the data was the image itself, because it's good enough. But now what we need to do is transform it. So just for the sake of the example, let's imagine that we are modeling into a table, which is an input that you can actually pass to a machine learning model. So we can start with like a very simple model, right? And we start with something very simple, and we will just assess and have it as a baseline. For that, we would create like a model that has, again, I'm going to be extremely simplistic, but what was the total profit of the transaction? So which address profited the most, and how much did it profit? And how many traces did the transaction have? So did someone profit a lot? Was it a complex transaction? That's like an extremely simplistic model of the data, but that's something that already allows us to keep moving into this, into creating this machine learning model. What is the next step? We have to collect a data set. We are going to use what is called supervised learning. Supervised learning, mostly what it means is you present the model with a set of data, and you are telling the model like, hey, you see this observation? This is bad. You see this observation? This is good. And you do that a lot of times, very iteratively, and in the end, the model learns how to do over that thing. So for that, what we did is we create this data set of previous attacks of the transactions that were actually subtracting the funds. But not only, you need to also have like good transactions to be able to differentiate them, right? So you create like this big data set with these hundreds, thousands of attacks, and these thousands, tens of thousands of Benning transactions. And then you train the model, right? Training the model here, and here is the deep learning model and not the data model. What you do is like you do this iterative process over a certain amount of epochs. I don't know how familiar with machine learning, but this is like standard procedure. You train, you have a loss function, and mostly the loss function, what you are doing is optimizing a function so that the model, what you are telling the model to be true, so these labels of the dataset that we commented before, it gets minimized, and the model has learned what you are actually teaching him. OK, now you have a trained model. With that, you can already defend blockchain. Yeah, sure. You can try, but then since we are like at the extremely simplistic point in time, we have like a very simplistic data model, it's not going to work that well. So what do? You go into evaluating the model, and you take millions of transactions of normal operations of several blockchains, and you evaluate that. And you see that your model is bad. Because at this point, it has not enough information to actually learn whether a transaction is good or bad, right? So then you go back to square one, and it's like, OK, I know that it's bad. How can I improve my data model? So you start thinking, you take a look at your evaluation, you look which transactions you fail a lot, and then maybe you saw that there are transactions where there are several people with profit, and in those ones you were very bad. OK, then you add a new variable to your model data, which is, OK, this transaction actually has 3 people on profit. And then you do again. In the collection data set, you already have a data set from the previous step, but you can use the most representative data points that you have collected during your evaluation, because that's the way in which you can keep improving your model. Like you evaluate it, you see where you fail, you tell to the model, you were wrong here, and the model says, thank you, and it won't do that mistake again. Then you train the model, go again to evaluate the model, it's a little bit better, you see another thing, and then you keep doing this iterative process until eventually you have a model that actually you're happy with the performance, and that it's actually able to detect attacks only using transactions. And that's super nice and beautiful, right? This cycle is something that it's called MLOps, which is the other keyword that I was missing at the beginning. It's like, this is the most keyword in ML after AI probably right now. this is literally DevOps applied to ML. So it's just a way of having like an iterative way of improving your models and monitoring them to make sure that they don't get worse over time, because that's something that can happen, and that you are still finding the stuff. Having this type of MLOps cycles is also extremely useful, because imagine that you are working with some customers, right? And then there is a type of false positive that it appears often. And here often means like once per month, right? But like once per month, you have one false positive with one of your customers, and it's always the same type of transaction. When something particular happens, your model gets confused, and it says that it's an attack, even though it's not. OK, doesn't matter. We have the cycle. We put it into our cycle. The next iteration of the model is not going to be wrong at that point. So it's a model that by itself, it's good. It's already able to detect a lot of attacks, but it's also going to keep learning and learning over time. And it's going to learn over the things that we are actually failing. So it's just getting better and better, and the things that we actually care about. What is the output of the model, right? Because right now, the previous slide was a little bit theoretical and was like, yeah, OK, the output of the model, what is this model actually giving us? Like in the example I was using before of pictures, if we are using computer vision, the output of the model is like, is this picture a cat or a dog? Is it a cat or is it a dog? But here we are trying to evaluate how risky a transaction is, right? So the way that we define them, because this is something that you have to define in the model, and it's something that you need to define when you are defining your loss function and your objective, and this is your end goal. What you want to do in a beautiful world is that every transaction that is an attack is at 1. Every transaction that is not an attack is at 0. Of course, that's never going to happen, because there's something in the middle, but that's the goal, right? So what we end up is like with this spectrum, and the model gets good enough when most of the attacks are as close as 1 to possible, and most of the no attacks are as close as possible to 0. Something that is also interesting is that since we are generating this risk score, and this is not only like a single value, right? It gives us like a complete interval of data. We can actually, depending on who is using it, they can decide how risk averse they want to be. Because some people, they want to be like, no, if you are even a little bit concerned that this might be an attack, I want you to stop it. Then you can say like, OK, everything that is over 0.5, go. You are going to obviously have a lot more false positives because, well, that's how things work in automatic systems. But you can make sure that you are not losing anything, because over 0.5, it's very extremely difficult that nothing is found. On the other hand, if you just want to make sure that it's a stop if it's like a very big attack and like the confidence is very high because you prefer losing a little bit of funds instead of annoying your customers, then you just go over 0.8, which is recommended value. That's why it's red. And then you will only stop like attacks that are very obvious attacks. So this is actually very interesting because it allows some configuration, even though it's a little bit esoteric at some point, but you can get like some understanding of how risky a transaction is, and you can decide based on your risk aversion. So now, this was the detection part, right? Like this is like when we were looking at the transaction, what we actually can say about the transaction being an attack or not. But I also promise you that we are actually stopping the attacks and preventing them. How do we do that? I'm going to go very low here. Like, I'm not going to go into a lot of detail because the point of this talk was mostly to talk about the detection and the AI that we are using. We have a workshop today at 3:30 where we are going to go more into detail into this. Otherwise, you can find either Andy or me. We are going to be around and we can explain a little bit better. But the main idea is like this, right? So a user sends a transaction. And the main point is that for users, don't need to know that they are already protected by Firewall, right? Like this has to be as easy as, like users need to know that they are a little bit safer, but they don't need to know how it works. It has to be as easy as possible. But it also needs to be very easy for actually protocols or roll-ups that actually want to implement this thing. So I promise you it's very easy, and like we are making it easier every time. We have a couple of different flavors of how this thing is implemented, depending on whether you are a roll-up or whether you are a protocol. It works a little bit differently, but like both of them are very low friction implementation. And once it's set, you can just set your threshold, and any transaction, all transactions are going to get screened, and the transactions that are over a certain threshold are going to be not executed. And it really works like this, right? So a user sends a transaction. It goes normal operation, as that user would be. The transaction gets screened at some point, like it gets outgoing a little bit to Forta Firewall. It gets analyzed. We decide a risk score for the transaction based on our machine learning model. Then the transactions that are over the threshold that the user, not the user, like the protocol user actually defined are dropped because they were too risky. And then they get logged. There is a dashboard. They can take a look at it, et cetera. And they can decide, no, OK, you were wrong here. You can, your next model shouldn't be wrong in these type of things. And the transactions that have low risk, so below the threshold, they go normally. The user doesn't see it because it's fast. So it's very seamless. And like most of transactions, most of them are never going to see any of these things. So I'm talking also a lot bit theoretically. I want to show you some numbers of how this actually works, right? And like the results that we are having with the model that we are having right now. First of all, like we did some tests on September. September had like around $40 million lost due to attacks. Out of those 40 millions, we detected 99.8% of the transactions that lost this money. So almost all of the attacks that happened were there. Out of 40 millions, we could have defended something like 39.9 million. It's amazing because, again, it's just looking at the transaction. We don't have any context. We don't care how you were founded. We just care what you actually promise that you're going to do. Like, I think this is very important to take home, that it's not about what you have done before. It's exactly what you have already committed to do in the blockchain right now that you are being stopped. So it's not about previous. You can do whatever you want before. What you are promising to do, because it's the transaction that you are sending at this point, it's the thing that might stop your transaction. So when you are showing that you want to steal those funds. Then regarding false positives, at the rollup level, so when we are analyzing all the transactions over a chain, we are having like one false positive around every 150,000 transactions or so, or better. But like, let's go one every 150,000 transactions. This would be, what, 10 false positives in the whole mainnet in a whole day. Like some other chains are like much better than this still. So this is not a lot of transactions. This is like, for example, Arbitrum. This is like almost 500,000 transactions. We had one false positive, which is the one that is in the red part. Like this is the risk score that I showed you before, just like a histogram. It's in logarithmic scale. Okay, like the one on the right is a 1, the one on the left is a 445,000. So if it wasn't logarithmic, we wouldn't see the risk 1. So that's why it's in this way. Then, for example, in base, we also have one that it's at 1, right? Yeah, casually, this was around the block when the Summer Money incident happened. So that's the transaction that was in Summer Money. So the only actual risky transaction that we have, and this is already around 100,000 transactions, is the one that was actually an attack. So this is something that we could have prevented. And then it works a little bit different when it's for protocols, because like they are more concentrated in the things they are doing, and like direct transactions are like easier to scan and so forth. And here, usually what you can expect is like to have one false positive around every 3 months. But let's be honest, like defending 99.8% of the money for just the pain of once every 3 months having to log out into your dashboard and say like, hey, this was not a false positive, that you know it's going to get improved over time, it's very nice. And this is like an example of one protocol that we are working with. So just for you to know that there are literally nothing even in the yellow and orange zones. So this is Forta Firewall. This was how we are using AI to actually start stopping malicious transactions. Anything that you want to ask us, like Andy and I are going to be around today. We are going to be around in DEF CON. Find us, speak to us. You can contact us by email, whatever you find. And yep, I hope you liked it.